I think my screen is now visible to you, right?
Yes, sir.
Okay. So can you quickly summarize what we did in the last class?
And layers of coding
Okay.
and information encoder, physical channel,
Okay.
all from decoder and destination, and all the interferences,
Okay.
all the interference, distortion, fading, attenuation, and we learned about fading, which is unique to wireless,
Yeah.
and all about 1 to 2.75G.
Yes. So I want to clarify one thing here that in the channel, as you said, there are noise,
Yeah.
interference, right?
This,
So this is
yes.
common to the wired channel also. But
Yeah.
in what we see that in wireless
Fading.
channel, we have this phenomenon, which make this wireless channel interesting.
Yeah.
Okay,
Multipath, due to multipath.
due to multipath, right?
Yeah.
So multipath is the reason, and fading is the phenomenon which we when we see that signal is changing very rapidly, we call this as a fading.
Yes, sir.
Now, till yesterday's lecture, we have discussed what is till 2.75G, right?
Yes, sir.
So next we will discuss the third generation of mobile communication.
Yes, sir.
The most common two most common 3G technologies are WCDMA,
Okay.
that is wideband CDMA, and UMTS, that is Universal Mobile Telecommunication Standard. Apart from this, we also have HSDPA, which is high speed data packet access,
Okay.
high speed downlink packet access. Excuse me.
Downlink.
Yeah. So these are the three technologies, or you can say standards, which are used in third generation of mobile communication. And this is a wide band system up to 2G, up to GSM, not 2G but GSM. CDMA is a wideband system, but GSM is a narrowband system.
Right.
And I will explain to you in the later slides that why we call GSM as a narrowband system. Okay.
Yes.
The operating frequency which we used around in 3G is around 2100 megahertz or 2.1 gigahertz.
2.1 gigahertz. Yes, sir.
What is the relation between giga and mega?
1,000.
Yeah,
10.
1000 times mega
Yeah.
is 1 giga. Correct.
Yeah.
So, what brings the third generation of mobile communication brings into on the table? It gives you. I mean, do you remember that before 3G, you were not able to do video calling?
Yes, sir. Yeah.
As soon as we got these 3G mobile phones, we started video calling. We started
Yeah.
watching YouTube, right?
Very slowly, but yeah. Yes, sir.
Yeah, very slowly, but because why it was slow? Because the speed was up to 30 Mbps.
30 minutes. Yeah.
So that point you can make it. That we can make a video call mobile TV if its speed is around 10 or something Mbps, right?
Yes.
But not very high definition TV. We cannot access high definition TV. So that is why we needed 4G. Correct.
Yeah.
Now
Yeah.
you yourself admitted that in 3G we could access only very small, very slow videos, and if you
Slowly.
want
Yes.
to access HD high definition videos, then we need more data rate,
Yeah.
right? Right.
Yes.
So in fourth generation of mobile communications, we had two technologies, which was two standards: LTE, which stands for long-term evolution, long-term evolution.
Long
Okay,
term evolution. Okay, sir. Long
just
term.
check those abbreviations or full form. Just confirm it. Sometimes, yeah, because I
Yeah.
have not noted it. And WiMAX is worldwide interoperability for microwave access. Okay, this
Uh,
standard, this WiMAX standard, is not much used. It's not very practical nowadays. But you see LTE. You
yeah.
have LTE enabled phone in your system. Just see your mobile phone, and at the
Yes.
very right corner, you will see VoLTE or LTE.
Yeah, I mean, in some phones it is present, sir. No,
Yeah,
I mean,
if you're
this.
mostly
Yeah,
nowadays,
yeah,
since we want to do this video conferencing, high definition mobile television, these type of services could be accessed only through 4G network.
yeah,
So I hope that I mean at least we have 4G phones now.
yeah. Minimum, maximum is 4G right now.
Yeah, maximum
Right.
in India. We have not
In
yet rolled
India,
out 5G,
yeah, in India we
but
have.
in
Yeah,
next 1 or 2 years we are expecting that. But in some countries 5G has been rolled out.
yeah, US
But
and
it's not like
yeah,
that once we say that 5G is rolled out means we have achieved full capability of 5G.
yeah.
5G will be rolled out in step by stages in many stages. Like the we will try to put some technologies over the 4G network which will enhance the 4G network and will be
Yes.
very near to 5G. I mean, they will satisfy the criterion for the 5G, and we say that we are moving towards 5G, right? So
Even
slowly,
4G has some problems. So it's
of course, 4G will
yeah,
have a problem.
yeah.
In 4G, we use OFDMA. You
Uh,
remember what was FDMA?
frequency division,
Frequency
multiple
division
access.
for
Yeah,
multiple access.
yeah.
But here we use a one more term that is orthogonal.
Orthogonal. Okay.
So, what does orthogonality provides you? Orthogonality says even the two signals are overlapping with each other, but they are orthogonal.
Right,
If they are orthogonal at the receiver, you can simply correlate it with some functions, which I will not tell you now, and you can get the two signals separately. If S1 is this, S2 is this, and if they are orthogonal, then you can separate them out. This is a
right,
very interesting property of orthogonal signals. Even though they are together, you can easily classify them at the destination.
right,
Okay. So in 4G, we use this multiple access technique. And slowly the rates is now hundreds of Mbps.
yeah.
Okay. And that is why it is called it is ultra wideband. 3G was wideband. Now we have ultra
Ultra
wideband.
wideband.
It's nothing but that how much frequency or how much spectrum does your signal takes. It's wideband.
Yes, sir.
As I told you that I would explain to you why GSM was narrowband. So as you say that now our phones are 4G enabled and we can see high definition TV and video conferencing, etc.
Yes.
Then why do we need 5G now? Do you
And
have any idea? Do you have any application in your mind which you think should be run in 4G network, but because
uh,
of its um, restrictions,
uh,
we cannot use?
yeah. I mean, these things. What is whenever we try to use an what is it? A
We,
network for
yeah,
hackathon in hackathon
correct.
robots or machines.
Yeah,
Uh,
if you have a large number of
yeah, and the
machines,
4G network.
very good,
Yeah, is insufficient for that.
correct. It
For
should be,
the information passing
yeah.
for the
And when we
machines.
use very low latency applications,
Means
low latency means if you switch your, suppose you put your data here, it should very fast and very reliable,
yeah. Till
very reliable.
even now the laptop glitches
Suppose you want
whenever you
to
use it.
do a robotic robot for operation,
Yeah.
robotic arm. So it should be very precise. You cannot expect that, okay, if I give you instruction that cut this
Yeah.
nerve and it will cut this nerve.
Command
Very,
and
very
yeah.
reliable, and it should be as soon as I suppose I am using my arm here and this is attached with a robotic arm, and the movement of my arm should be replicated by this robotic arm,
Yes.
correct? And this
Yes.
will apply surgery here for the for a person,
Yes. Sir.
correct? So as soon as I force my finger to cut a nerve, it should also do the same here. So
Yeah.
very reliable, very
Precise.
precise, and that is why it is called ultra reliable and very low latency, right? Similarly, this
Right.
type of requirement is there for the vehicle to vehicle communications also. and data rate. And if you are seeing that 360-degree videos like online gaming, very high data rate applications which require we are moving towards gbps now.
Yeah, gaming also requires much faster. Yes, sir. I do
Correct,
play. Right, right.
correct. So in the next generations of the wireless communications, we will be able to see this type of application in the practical scenario that this will happen.
Right.
Okay, so this will be your home assignment as tomorrow and day after tomorrow you have a holiday. So I will just briefly explain few of the technologies. So what would make 5G happen? There
Uh,
must be some new technologies which must be involved, which must be used over 4G network in order to make this happen, right?
yeah.
In order to realize 5G networks, we have to use few technologies. So one such
I
tech,
don't understand, sir. I mean, you are saying what is the tipping point for 4G to go to the 5G or like that something?
no,
I mean,
no.
yeah. Please tell again.
Just you have understood that we want to
Move to 5G. Yeah.
move to 5G. Then what should you do in order to move to 5G?
Right.
What changes you have to make? You have to
Oh,
use
okay.
new technologies
Yeah.
to enable this 5G
Yeah.
network, to realize this 5G network.
Okay.
So one such technology is massive MIMO.
Yeah.
It implies that you should use massive number of antennas at your base station, and there are many users. So this technology will help you provide all the benchmark which you want to achieve in 5G, like high speed and low latency and other things, ultra reliable applications.
Right.
Similarly, we have D2D communication that is called device to device communication. What happens in device to device communications? Suppose you and your friend communicates with each other frequently,
Right.
correct?
Yes, sir.
And you live very nearby. Suppose you live in first floor, your friend lives in second floor. You always chats or you always make some conversation over phone. So what it would happen that you will first make a to first you send a signal to base station, and then this
Yeah.
base station sends you it.
Yes.
So base station is saying that these people are lives very slow. I mean, very nearby. Why are you wasting my time and why my resources? They can communicate with each other without help of me, without
Yeah.
taking my help.
Yeah.
So that is called device to device communication.
Yeah.
We throw away the use of base station and we try to develop algorithms, protocols, or something so that these two devices can communicate with each other without taking help from the base station.
That that would require multiple for each device or
Yeah,
each device. Yeah.
each device first searches if it lies
Yeah.
in the vicinity. It will
Vicinity.
say, okay,
Yeah.
we don't need now cellular network, and it
Yeah.
switch to a D2D mode.
Yeah.
It will first it was in cellular mode, for example. Now it will switch to the D2D mode, and you can communicate. And once you want to communicate with someone else, then it will again switch to the cellular mode.
Yeah.
Okay, so this is called D2D communication. Similarly, as you said that in 5G we will be having massive number of devices connected with each other. So there will be a problem that each device will consume lots of energy
Yeah.
in the form of battery.
Yes, sir.
So what researchers suggested that why can't we harvest some of the energy from the RF signal?
Harvest like
Harvest,
plants, sir.
that is called, as you say, that is solar. What happens? Solar
Yeah.
cell. What solar cell does? Solar cells
Harvest
receive
from energy from sun.
sun. Correct.
Yeah.
Similarly, it was suggested or it was researched that can we harvest some energy from the radio frequency signals which are there in the environment, as well as when we transmit radio frequency signal from A to B. Can we harvest some of the energy here?
Yes.
So yeah. So this thing has been already developed and is in progress also. So this is one technology which people are suggesting that 5G should use.
Okay.
Okay. One such technology is cognitive radio. Okay. So what is cognitive radio?
Uh, no ideas.
Okay. One I will just make a slide. In cognitive radio, what we do, as you said that the resources in 5G there will be many number of devices. So the spectrum, the channel will be very scarce, right?
Sir?
The channel or the spectrum, the frequency available will be, we want to use it very efficiently.
Yeah.
So what happens in cognitive radio, some of the users just sense if particular frequency band is available, then they will use that frequency band for that moment only. When primary user for some for because of some reason is not using that resource, this is a primary user.
Yeah.
Okay, so we have a priority will be to give resource to this user only first. What secondary user does, it continuously tries to sense if a particular portion of spectrum is available, because this is a secondary user.
Right.
Suppose he has just typed a message and if it goes now or 1 hour later, it doesn't matter. It will just, whenever the spectrum is available, this will go, right?
Right.
So if such type in, so what happens for any reason, if primary user is not using particular spectrum, the secondary user just sense it and then will utilize that spectrum.
Right.
So this is called cognitive radio. I'm giving you very a brief. Uh,
I mean, what designates as primary and secondary, sir?
we, according to the application, we first define that it is our primary user and it is our secondary user, because the service which it's asking is more important than the service the secondary user asking.
Right.
Okay. Similarly, as I told you that there were three type of access techniques we have discussed, right?
Right.
EDMA.
TDMA, FDMA, CDMA.
Correct. Very good. So now what researchers are trying that can we use some other access techniques also, which is not orthogonal. The TDMA was orthogonal in time.
Non-orthogonal multiple access.
Very good. You know it, right?
I heard of.
You heard of it. Okay, very good. So TDMA, FDMA, CDMA, it was orthogonal in time. This is orthogonal in frequency, and this is orthogonal in code.
Yeah.
So recently in 5G, people proposed that we can transmit the signal over the same time resource, same frequency resource, and even the codes will be, I mean, we will not give them orthogonal codes. But we will soon use some intelligent technique at the receiver end so that we can extract the information. So that is called non-orthogonal multiple access techniques.
Uh, Intelligent technique means, I mean, it's a
Uh,
way.
okay, so what happens? Sometimes they will, if you want to transmit information x1 to x2, right?
Right.
So first we will transmit x1 plus x2. Suppose we superimpose the information of both the user and transmit it. Then
Okay.
what happens? This user first decode his signal and the other user signal also.
Yeah.
And then what happens? It will give this signal to the the secondary user will receive x1 plus x2 and it will subtract the information of the first user.
Okay.
So this is an intelligent thing which they cooperate and they do.
Okay.
So I'm just giving a brief overview of these technologies so that you are, I'm just encouraging you to read those technologies and understand and write something, a few paragraph. And if you have any query, we'll discuss.
Okay.
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 Do you find it interesting? These
Yeah.
technologies?
Yeah.
Just try to write few paragraph and if you have any doubt, you just highlight that and we'll discuss it.
Right, right.
And once you make your PDF, you can submit it.
PDF. I mean, I will write it and then make
Yeah,
it
it
PDF.
says it's an assignment, right?
Right.
Okay, so
Fine.
you have to submit it.
Right.
So this, because you have a 2 days, so this
All,
will be
all, all, all these things. If you
okay. You do
or
one
to,
thing. You
uh,
read all of them. You write one paragraph for each, and if you and select any of the technologies which you find interesting,
yeah.
okay, and write more about that
Okay.
and ask questions.
Yeah.
Okay.
Yeah.
So next we will discuss three things. You remember that we have modeled our wireless channel as a multi-path channel, right? The
Yeah.
summation of deltas. So now we will do it formally. There we have just discussed it for the sake of discussion, right?
Yeah.
I just check whether I have started recording or not.
You did.
I did. Okay, great. So here we will formally model the wireless channel. We will also characterize or write mathematically what is the transmitted signal, and then we will see that what should be the received signal when we transmit this signal through the wireless channel. We just model it here, suppose, and when what receive, how should we write it in mathematical sense. Okay.
Yeah.
So let's first suppose you have a base station here, right? You have a mobile unit here. So there are, as we discussed there, that there are tires, cars, buildings. So your signal propagates. So how you model a channel, or how you do you model a system? Remember this thing?
Uh,
Remember
yeah. Impulses.
impulse response. What is the definition of an impulse response? Just try to recollect what you learned at your in your undergraduate.
Mm,
You provide a delta signal to a system. It should be a linear system. Just I'm just giving you a hint because impulse response is defined for the linear systems. Just you have gone through your signal system course. Just try to recollect it. So when we provide delta signal, the output of this system is impulse response. Okay.
yes.
So we will try to find out what should be the impulse response of this wireless channel, because this is nothing but a system, right? You can put in a black box,
Yeah. Multi-path system.
multi-part channel.
Child.
Yeah. So here you provide input, and at the here you get the output, right? So
Right.
if you provide delta t here, what is your ht? Should be your impulse response. Correct. So this is our aim, to characterize this wireless channel as a linear system, and what should be its impulse response, ht. This we want to find out.
Yeah.
So when we send our signal from a base station, as I told you, that it follows multiple number of paths. One path is direct path, maybe it may or may not be present, but if it is, then we call it line of sight loss path. Correct?
Yes.
And other paths are non-line of sight. Okay. So let's we
Yeah.
call it a zeroth path is first, and similarly other paths, and this is the lth path. Okay.
Yes.
So, as we discussed, the impulse we get superimposition, right? The received signal from the many paths or the multiple paths interfere or here superimpose with each other either constructively
Or yes.
or deconstructively. Okay.
Yeah.
So if the attenuation from the first path is A naught and the delay introduced by the loss path is tau naught, similarly we can write what should be the delay of this path tau 1. The attenuation of the lth path is AL and tau. And all of them adds up at the mobile station. So just add it, right,
Yes, sir.
Surya?
Yes, sir.
And we just write it in this form.
A
What should
delta
what should
T
be left?
minus tau naught. T
Tau,
minus I.
correct. And I will move from what should be the index here?
0 to L.
Very good. 0 to L minus 1
1. Right.
because it is Lth path.
L
So
path.
I
Yeah.
should write it L minus 1 here. It is just a matter of index. You can start from 1. If you say loss path is first, then it will become
1
L.
to L. Right.
It's just matter of presentation,
Yes.
representation. So now you have characterized your wireless channel, correct?
Yes.
So first aim is complete that our line of sight channel. We have modeled our characterized our wireless channel in this form, and this is the impulse response. Correct. What was the next aim? How to model the transmitted signal.
Right. Right.
In
Transmitted
this.
signal. Wireless channel. Transmitted signal. Right.
Because whenever we study any system, we just see the input, the output,
Output.
and the impulse response. For any linear system, we just study this type of block, right?
Yes.
Okay. So let's model our transmitted signal. From digital communication course, if you remember, that we can transmit our information in this form,
Yeah.
that in phase, and we multiply it with the right.
Yes, sir.
Then there is a quadrature phase, right?
Yes, sir.
This is your signal which goes into the channel. So we call it a pass band signal. Why do we call it a pass band signal? Because it is
It's located
centered
F
around
single bar.
no, it's
Single.
centered around
Located away from origin.
it is centered around a frequency which is quite away from the
Yeah. It's
origin. It's a
located away
pass
from
band
origin.
signal. It's not baseband. It's
Yeah.
pass band signal. So we can represent any pass band signal in an equivalent baseband representation. This is a very important topic which is called pass band baseband conversion. Baseband. Sorry. Pass band to baseband. Okay.
Yes.
So if I say I can write my pass band signal as PT as real part of XIT plus JXQT multiplied by e to the power j2 pi FCT.
Okay. Right.
And
Right.
you can do it, just multiply it with this first, write it as cos 2 pi FCT plus
Plus
j
I sign.
sine 2
J,
FCT,
J sign 2 by FCT.
and then just extract what are the real part of this signal. XIT multiplied by cos 2 pi FCT. correct?
Yes, sir. That's
Here I have done
exciting.
that.
J,
So
J, J.
you
Cost
can,
by FCT minus, yeah,
other
exciting.
is imaginary. So just we are saying here that we are taking real part.
Real part. Yeah.
So any passband signal of this form can be equivalently represented by this real part of xbt e to the power j 2 pi fct, right?
Yes.
Where this is a xit plus j xqt, correct?
Yes.
You can put q here. So this is called baseband equivalent of your passband signal. This is done for the mathematical point of view, as well as we see that what is happening here, we are just up converting this signal, right?
Yes, sir.
So if we just do all the mathematics over here, then it is just multiplication of some factor, so it helps out. It's analytically more, I mean, better way to do that. Okay.
Yeah.
So now we have understood what is the structure of your transmitted signal, correct? Now you know
Yeah.
the transmitted signal is, if you want to represent your, sorry, again my pen, sorry, I have
It's
to,
fine, sir.
yeah. Hmm. I don't know why it started like this. I will just close it once and then we'll start.
Yeah.
So here it was, if we want to represent it as baseband, then we can say it is baseband. This is passband signal. So baseband equivalent is this, right?
Yeah.
And we can convert this from this equation, right? So as you know, this is your HT, this is your passband, and this
Pass
is your
back.
HT. Now what should be your YT? Do you know? Do you remember the term convolution?
Yeah. Yes, sir. Yeah.
So what we are doing here, we are convolving the input signal.
Yeah. H of t into x of t minus.
This is your impulse response, and this is your passband signal. Because at the channel you are putting this, the input is XPT, your passband signal, and HT, and this is your YT. So we'll see how we can represent YT as the baseband equivalent. And now we know that this is your baseband, right?
Yes, sir.
So your XPT is this.
XPT.
Just take a little time so that you're not confused. See, this was your input signal, right?
Right.
Just think it like that. We can represent it like this also. That's it.
Right.
Okay. Now forget everything else. That your passband signal can be written it like this, because you know that you can write this also as like this. Okay.
Yeah.
Okay. Let's move it like that. So we can write your XPT as this, where XBT is defined at in phase and plus J times quadrature phase. Correct.
Yeah.
Now
We.
what should be your YPT, or what you receive at the receiver? This is the convolution, right?
Yeah. Convolution.
So just convolve. Use
YPT.
this equation, replace t with t minus u, and just do the integration. So once you do it, you can take its real part here.
C t minus u and h of u du.
Understood?
Yes, sir. Yes, sir. I'm just
Okay.
copying.
Okay, copy it. Take your time.
Okay. You just separated e power j to pi of ct, sir.
Correct, right.
Yeah.
And since it does not depend on you, we can take it out.
Yeah, it doesn't depend on you. We can take it out. Yeah. Constant. Right. Copied, sir. Yeah. Continue.
Copied? Okay.
Yeah.
So just compare now this with this real part of some ybt into e to power j 2 pi f ct. If we define this integral as ybt, can we write ypt like this?
Yeah. Yes, sir.
Okay.
IBT. Yeah.
You can write
Yeah.
it, right?
Yeah.
So what is the baseband equivalent of this ypt? This integral.
The whole integral. Yes, sir.
Okay. Correct.
Gabbard was away on active.
So this, but we have not replaced HU rate, right? What was the impulse response of the wireless channel? Summation of many deltas here.
Yeah.
So now we will do that. Now I will just first summarize it once so that you are more comfortable. Till now, what we have seen, this is your XPT, correct? Which can
Yes.
be
Is
represented
real.
like this.
Yeah. XBT
This
power
is your
j
channel,
to pi of ct.
which is AI del t minus tau I, correct?
Yes, sir.
And you receive YPT, which can also be written as like this, right? Where we
Yes.
have given YBT as.
YPT is equal to YBT.
Have you written it?
Yeah. Yeah.
Yeah,
Real part of.
just speak it out. Real part of. No, no,
E-
I am saying YBT.
Right. Right. I'm copying that, so that's why I'm just.
You are again copying it. I think you have already copied this equation, right?
Uh,
This is the
I yeah, but a thorough understanding is required
okay, okay, great.
for me myself.
I'm just
Right.
summarizing whatever we have done till now.
That's fine.
So what was the YBT?
Uh, yeah, that one, sir, says sigma. Yeah,
It's not sigma, it's integral.
integral xb t minus xb t minus u h of u e power minus j 2 pi f u u du.
So if somebody asks you what is the received signal and what is the transmitted signal, you know its baseband equivalent. You can also answer in baseband equivalent because see,
Yeah.
here you have XB, here you have YB. And you know how to convert your baseband to passband.
Yes.
So why not just read or study this, right? Because
Yeah.
once you know that this is your baseband equivalent of your what you have transmitted, then what is the baseband equivalent what you have received? And then just multiply it with this and you will get what you have received in reality,
Yeah.
right?
Yeah.
So the baseband conversion I mean, I will just give you an intuitive. Why do you think we should convert a signal to first baseband? It's a mathematical. I'm saying that you can do that, but it's also have some practical importance. See, you have a high frequency signal, right?
Yeah.
You can sample it and you have to save it. If you want to save this high frequency signal, you will use a large space because your samples will be more, right?
Yeah.
But what if you can convert it to a baseband which is like less frequency signal, because we have now have removed this term, right?
Yes, sir.
High frequency component, so the samples will be very less. It will become like this, and they are equivalent. You can just convert it from here to here. So why not do all the processing in the baseband?
Yeah.
You
Yeah. Why?
understood? That is why you heard we up convert the signal at the transmitter and the receiver, we down convert it, and we get baseband signal here. Here you have baseband signal. You multiply, you send it. And why do we use high frequency in order to send at the wireless channel? Because if you remember from your wireless course, we use higher frequency
Yeah.
so that we can get more rate.
Right. Bit.
Do you get what I'm saying?
Yes. Yes, sir. Yes. Yes.
Higher the frequency, suppose you are operating at 10 megahertz.
Yeah.
Sorry, okay, 1
100.
megahertz.
100.
1 megahertz, for
Yeah.
example, and now you are operating at 1 Gbps, and you are allocated 1% of this band, 1% spectrum around this.
Yeah.
So its bandwidth, see, its bandwidth is very low because it is in term of megahertz. But here
Yeah.
the bandwidth high because you are in the gigahertz range.
Gigahertz. Yeah.
You can transmit more information. So we generally move from higher frequencies. That is why you see what was the operating frequency of 2G and 3G?
2G
Two,
and 3G is
GSM,
900
yeah,
for
900
2G.
megahertz.
3G is 220, 2.1 gigahertz. I think.
Correct.
Yeah.
So yeah. So now we can operate on the baseband only. Correct. What
Right.
is the baseband equivalent of your received signal? Correct.
Right.
Okay. Try to grasp whatever you can. Then read it out in the. I mean, then we can discuss.
Yeah.
So now we know that this is your baseband signal.
Right.
And what was HU? This was your HU, right?
Yeah. Yeah.
Impulse response of the channel. Then you just replace it here.
Delta.
Okay, and then we can just swap this integral sign and summation sign, and then we can write this integral like this.
Right.
And do you remember one property of delta signal?
Property.
Del of is nothing but ft.
F of t. Right.
Remember?
Yes. Yes.
So use this property here. Understood?
Yes, sir. Yes.
Once you use this property, you will see replace u is by tau I and you will get this.
Yeah.
Okay. So this is your baseband for the baseband signal, baseband received signal for the wireless channel, which can be modeled like summation of many multipath channel, multipath components.
Yes.
So this is your final expression that your y dt is What was the expression?
Integral of
Not
xb.
integral, just be very now, since
Okay.
we are moving from classes, I will be more particular. You should not make these mistakes from now on. Okay, try to be. It should be
In,
summation, like it's not integral.
okay, okay. Only you're asking for integral that one, right?
No. I'm just saying that
No.
it's okay. It's no problem.
Okay.
Okay, so we are saying that
Sigma.
yeah, sigma or summation sign.
Yeah, summation
Summation
AI
AI
explain
xb
e minus tau I
great.
e power minus j 2 pi f c tau I.
So this is your received baseband signal.
Yeah.
Okay. So I have written here narrow band assumption. So I already in the beginning of class told you that I will explain why GSM is a narrow band
Narrow band.
technology.
Yeah.
You remember that?
Yes, sir.
Okay, so let's discuss it. In GSM, each subscribers first it was around 1000 megahertz, 900 megahertz, right? You remember?
Yes.
And their first use only they can only use 200 kilohertz. I mean, many users first given different bands, and then in each band we do TDMA, right?
Yes, sir.
You can just go through a GSM when. So you can see that the channel, that the total bandwidth is around it's 200. Okay.
Yes, sir.
So GSM pass band signal has this type of frequency spectrum. So the baseband when we down convert it, it will have like this type of frequency spectrum baseband for the GSM, right? Something like that.
From
That
pass band to base band, right, sir?
yeah, we're just converting to pass. I mean, just we are down converting.
Down converting. Yeah.
When we down convert, the maximum frequency component of the baseband signal is FM, for example. So what is the FM for this XBT? Sorry, this is not Y, this is X. This is the transmitted.
Right, right, right.
Right, sorry.
This is XBT.
So for the GSM, the maximum frequency component of the transmitted signal is around 100 kilohertz.
Yeah.
So we say a signal is narrow band if its maximum frequency is less than 1 upon delay spread for every I. Do you remember what was the delay? Delay, it
Yes.
should be delay. Ith path. Delay of the ith path for every I. The delays were like this, right? This path when we transmit,
Yeah.
this was the base station. It is a mobile station. It was first path, zeroth path, 11th path. So the maximum delay for every I mean the delay, the maximum frequency component satisfy this.
So maximum frequency component should be less than 1 by delayed path.
Then we say that our signal is narrow band. So FM is around 100 kilohertz,
Yes.
and this tau I is generally in the microsecond, 1 microsecond.
Yeah.
So you can see that this inequality is satisfied.
Yeah, yeah.
So that is why we call GSM as a narrow band signal. Okay.
Yes.
So GSM is a narrow band technology. It was an example of there are some other technologies which are not narrow band like CDMA, and we also discussed WCDMA, LTE, right?
Yeah.
These are not. So once we have this signal YBT as summation of AI XB t minus tau I, or minus j 2 pi
L
c tau
xp
y.
t minus tau y.
You can remember it
E-
like that. This is a attenuation of the ith path. This is a delay of the ith path,
yeah,
and this is a phase introduced because of the delay.
yeah,
You can remember it like that. Okay, you send a baseband signal from here. Now you can, because see, this was up conversion, right?
yeah,
And here was wireless channel. Here was down conversion, and you receive YBT after
yeah,
down converting, right? Here you have YPT. Here you have XPT, right? So you can see it like now this, like this. You can just correct mathematically. You can see like this. That you understood?
yes, sir. Yes,
Okay. So this was your baseband signal, and this was your baseband receive signal
yes,
after
minus
down
LC.
conversion.
Yes, sir. Up convert and down convert.
Yeah, because and also I told you why we should do that, and mathematically we have seen that it is not a problem. We can do that. Okay,
Yeah,
and we can do all the analysis in baseband only, and we can just see that it is just transferable. So why not just do it in the baseband to
yeah,
understand analytically also, and it is practically also I told you why we should first convert to a baseband signal because it
yeah.
is less because the frequency is less, so the operation also requires less number of cycle, and the storage
Frequency
also,
is also, yeah,
yeah, storage will be also less.
yes, yeah,
Okay, so once our signal, the maximum frequency which is there in xbt is less than 1 upon tau I for every I, it is called for every, right?
yeah, yes,
Okay, so we can call it as a narrow band signal, and for the narrow band signal we can simply take this approximation. Do you understand this approximation?
right, sir, right, yeah, yeah,
So do you have another class after that?
yes, sir.
Okay,
No,
so
another
we
plus.
will finish till now.
Yeah,
This happens due to the narrow band assumption,
yeah,
and we will start from the next class that after narrow band, once we have narrow band
sir. I
assumption.
won't be available on Monday. I'm going to write an exam.
Exam. Okay.
Yeah.
So on Monday, whenever you are free, just
I
message me.
mean,
Not the
till
whole
you,
day.
not till evening, sir.
Okay.
Yeah,
So we can do it in the evening then. Okay.
yeah. I mean, yeah,
Or in the Tuesday
depends.
if you are not available.
Yeah, Tuesday is fine, sir. Monday,
Okay, we will do that. Okay, sure. Okay, so we
right?
will start from here tomorrow. Okay.
Yeah, yeah, right. Bye, sir.
Oh, yeah, yeah, sure.